This is a part of a larger work that we are doing in diagnostic mechanics. Research group is indicated here. A special thanks to Davide Palumbo and Rosa De Finis that actually worked with me quite a long time about this, the subject of this presentation. Here you can find my email for eventual further contact if needed. So I will start with a short introduction about what we do actually in terms of thermal methods, above all applied for additive manufacturing components in my lab. Then we will start to think about what happens when damage is occurring in the material. In order to introduce the energetic methods for the fatigue characterization, I just jump at the fast word, because it's all the issue here is to have a fast response in terms of fatigue characterization of material. Then to explain which are the thermographic methods that actually are available to do that, and some example of the really large application, the large number of materials, very different kind. Then the added value, the latest added value is the moving from the fatigue limit evaluation to the entire Wooler SN curves. And then let's try to draw some conclusion. Okay, in my lab, I mean, we do a lot stress analysis, experimental mechanics, and non-destructive testing with a lot of techniques, quite a variety of techniques. But I have to confess that the thermal methods are actually our diamond point, because I have been working from that since my thesis in 1992 in terms of stress analysis, and I kept going, setting up the labs in 2008. So we work a lot in terms of stress analysis, above all application development of stress and thermoelastic stress analysis application for NDT, for stress measurement, for damage assessment, for residual stress evaluation. Then also we do a lot of mechanical characterization of material with traditional, of course, and innovative method, a lot of thermal methods, and we will explain later on much better. Some fracture mechanics with the thermal methods. So we set up procedure for obtaining directly the Paris law of material with a thermographical assessment. And also the possibility to assess the stress intensity factor via TSA. A lot of non-destructive testing, some in composite component, a lot in composite component, but lately in the last 3 years also in additive manufacturing. So in terms of additive manufacturing, especially in additive manufacturing, we are collaborating with BAM of Berlin in order to obtain, to study the feasibility of thermographic NDT to analyze what's happening in an additive manufacturing component. So we got some, an example of some defects inserted on purpose, or at least we try to insert on purpose. The defect inside is quite a straight sample, and so we obtained very good characteristics that had a very consistent comparison with the radiographic method, CT, and we obtained possibility to measure and characterize also some pores and keyholes. And some process monitoring, working with some industry. Here we have a laser passing on metal, and so we can, of course, monitor with the thermographic analysis what's happening to these lasers. So we can actually have a lot of possibility, a lot of information about how the process is in control and what's going on your material. And here you can find a picture that some of the audience will recognize from work a very long time ago. This is a finite element analysis of a car engine bracket, and this is a stress analysis obtained with thermoelastic stress analysis. And you can see the consistency of the data, and the beauty of this method is that you can obtain results in terms of seconds. And so you can obtain the results while the fatigue testing is actually running. If we want to, let's say, understand a little better what's happening, what is thermoelastic stress analysis. This is a thermographic video of what's going on while you are performing fatigue testing on a sample. You can see this flickering here. This flicker here is actually, okay, is actually temperature variation, is a pixel temperature variation. And you can see that this temperature is actually following the load. And in fact, if we want to, if we start from the first principle of thermodynamics, we come up with the relation of that the temperature change of a solid body is related to the change, it's an assumption, to the change of the volume of the material. It means that it's related to the change of the sum of the principal stresses. So if we make some assumption, local adiabatic condition, and there is because we have a high frequency load, homogeneous material, a small temperature change, whatever, we come up with a very simple equation. Temperature variation. Maybe you don't see my mouse. Okay. The temperature variation that we obtain during loading is related to the load. Actually, there is a minus sign because if we compress the solid, then we heat up the solid. When we delay the solid, actually we are cooling it down. And so we can use actually this stress analysis for a fast a comparison with finite element analysis. I've seen a presentation before of the fatigue testing actually carrying out on an optimized structure, and it would be really interesting actually to have a real-time stress state of the material during the testing. Here you can see there's another very lately application on additive manufacturing in terms of stress analysis. We're working with the University of Messina about this. This let's say, processes that is put in some vertebra if you have some problem with your spine. And you can see that you can get very easily a stress map of this trabecular structure. There is a bending moment here, and we are actually performing quite a number of structural analysis to understand how this trabecular is actually working and which are the best parameter for the structure. I'm here to propose you some, or at least to introduce you some new advantages in terms of thermal methods for material characterization. So what's happening when we perform a fatigue test? The temperature of the solid body will change because there is a heat exchange, and also because there is energy dissipation due to the fact that we are damaging the material. Then there is also the thermoelastic source that we just introduced, and also there is an internal coupling of the mechanical parameters. If we actually make some assumption to simplify the equation, we come up with this equation that relates the change of temperature of a solid body to the heat exchange with the environment, to the energy that is actually dissipated inside the material, and the thermoelastic source that actually, as you saw before, assume the form that you can see in this equation. What's happening when we are actually performing a fatigue testing and we are damaging the material? We are not just below the fatigue limit. So you are giving some energy to the material. You are forcing the material to the format to store some energy, but also you are forcing the creation of damage, and then after all the creation of surface failure surface, and an hysteresis loop will come up with a shape that is actually related to the load and material state, and eventually to the change of material characteristic with time. But I mean, you can hear that, which is the energy balance. The Q is the heat exchange with the environment. So if we have local condition, we can, or at least we can control this. And then we have two terms. The first term that is actually related to energy of plastic deformation. The second term that is actually the energy dissipated as heat per cycle. So the idea is, okay, so if we have a damage, then we have a heat that actually come up at a heat source that is inside the material. So what if actually we can monitor that heat source in order to have information about the damage? This is actually the basis of all the method that actually have been developed during this year. Just to simplify, let's assume, let's analyze what's happening to a perfect elastic and perfect plastic body. It's just a simplification. You can put there any kind of hysteresis loop. The concept will not, the idea will not change. So what's happening here? Of course, stress and strain will show a phase because you are actually experiencing a different time law for stress and for strain. And because actually dissipation is occurring, you are setting a viscoplastic regime. And the interesting part is that going back to thermoelastic analysis, this actually will come up. Here we have what's happening when everything is fine and everything is in the elastic condition. But when actually we are damaging materials, we have also some plastic work there. There is also a shift between the temperature and the load. And so we can monitor this phase shift. This was the basis of thermoelastic phase analysis that we set up now 10 years ago to monitor the damage occurring on welded joints. And of course, if we are damaging material, the linearity that we set there is not valid anymore. So the lack of linearity of the thermoelastic response is also a possible way to monitor the setting of a damaged state inside material during fatigue loading. Okay, during fatigue loading, we are assuming that we are showing as a scheme this kind of hysteresis loop. When we ask ourselves what's happening in terms of energy and then in terms of temperature, of course, during the elastic load, nothing is happening but the thermoelastic effect that is fully reversible. So it's not actually giving any contribution to the increase of temperature. But when we go to the plastic area, then we see an increase of the energy that we are putting inside the material. That corresponds to an increase of temperature of the solid body. Then again, the elastic part, we don't experience anything but the thermoelastic part that here is not represented. Again, a change of the energy stored and dissipated inside the material, and again, the elastic part. If we see at the temperature, this means that in a cycle during the fatigue load of the material, the temperature will experience a change in this way. It means that there is a change of the mean temperature of the overall specimen, and also there is a double load frequency change of temperature that is related to the dissipation due to the plastic work. And of course, according to the shape of the hysteresis loop, I mean, you can have different terms in the fast Fourier transform of your function, but the main part of plastic work is actually detectable and measurable by the second harmonic temperature variation, the second harmonic in compared with load. Okay, so there is actually, this is not new in terms that, well, at least the temperature changed, because first work go back in the 80s, so it's quite a long time ago. There are different approaches in these thermal methods or energetic methods, energetic approaches by Padova and ourselves and other university. I must say that the Italian school of energetic methods is actually very strong, internationally speaking. There's the temperature monitoring, that it was the first one to be set by Luong and Risitano. And there is also everything that we set in the last 10 years about thermoelastic stress analysis and monitoring of the damage. So this is actually the framework of the work that we are doing as energetic methods of the AIAS, that is the Society for Stress Analysis, actually is the society of our in Italy, and we set up a group of 8 universities, and we're working, let's say, working on all these approaches. Today, I want to focus, well, we use all the approaches that are actually in the bold character, but today I want just to show you something about the ones that are in the red character. So linearity of thermoelastic analysis, second harmonic, above all second harmonic, and thermoelastic phase analysis. So what's happening when I load a material? Here you can see a specimen. Then it happens that you saw it before. There is a change of the mean temperature of the specimen. Then there is an heat exchange with the environment. So there is a plateau, a kind of plateau. You can see there some experimental data. Down, and when you are just breaking, I mean, abruptly breaking the material, you will have a sudden increase of temperature. But if we monitor this, okay, we monitor this, we come up that with the idea that there is no change in this temperature if nothing is occurring. So we are below the fatigue limit. Then we are starting to see something is going wrong or something is going differently from the elastic behavior of the material. It means that some damage is occurring, and then this damage is more and more with the higher load. First attempt to analyze, obtain the fatigue limit is just to cross these two straight lines. I mean, we are experiencing a lot of discussion about the meaning of those. Also, the analysis of the ramp, this ramp, actually, this temperature change rate, it is a possibility to obtain the fatigue limit simply putting the value of this ramp and then going backwards to see when actually this ramp was set. The idea in Bari was slightly different. Okay, why we have to focus the attention only on temperature? We show that what's happening on a component while we are experiencing fatigue testing. So why don't we actually use all these parameters? The change of the mean temperature, the lack of linearity of the thermoelastic response, the phase shift of the thermoelastic response, and above all, the second harmonic temperature change that is directly related to the plastic work that actually is in the material. And actually, also because this is something that actually we have been working for a while, and we are obtaining good results in terms of thermal SN curve. If we measure this second harmonic temperature, you can actually estimate which is the plastic work that actually we are putting into the material without the need of an extensometer or without the need to measure it in elsewhere way. Which is the importance of this? Well, okay, if we are talking about coupons, then there's no problem. All methods are fine. But if we are talking about components, components will experience stress concentration factors, will experience maybe some cracks, and then the cracks is growing. So it's very difficult to, unless you use experimental stress analysis or a hybrid technique with finite element analysis, very difficult to use the thermal information on a component unless you have a local information like double frequency temperature change to the plastic work. This is just an example of the kind of results that we obtained. These are 3 specimens. This is the mean temperature change of this C45 steel. Very easy to monitor also in terms of temperature. So you can see there's nothing is happening, and then the fatigue limit occurs, and then we are breaking the material. But also the phase shift showing the same results, and the lack of linearity of the thermoelastic stress analysis and the energy dissipated. All of those are giving the same information that are all very consistent by themselves in terms of above all of fatigue limit evaluation. We have been working with a lot of materials. Austenitic steels are very easy to monitor because basically they are the chewing gum. I mean, they really have a huge plastic work, and so huge heat coming up for it every cycle. But we have been working also a lot on martensite steels that actually have a much lower temperature variation, and aluminum, composite material, and for all of them we got very good results. These are a comparison in terms of C45 steel. This is just an introduction to the use of double frequency temperature change for the SN curve. So we saw those before. This new curve is actually the energy that was measured inside the hysteresis loop that was recorded by an extensometer and loaded by the loading machine. For two stress ratio, R01 and R-1, much better results, much signal. The fatigue limit evaluation that is becoming trivial, but this is actually the interesting part. Okay, if we focus the attention on the information that we have here in terms of hysteresis loop measured and in terms of the energy dissipated estimated by the second harmonic temperature variation that is related to plastic, then we obtain these two graphs. Okay, so it's interesting because I mean, we don't have a full overlapping of the curves, and this is normal because actually the second harmonic is not the only harmonic that is actually inside this function. So it is not the entire energy of plastic work that actually is showing up in terms of temperature variation in second harmonic. But if we actually put the information together in terms of delta W measured by hysteresis and the energy dissipated estimated by the temperature variation, you can see the fantastic linear correlation that we have between the two information. It means that actually if we calibrate the signal, thermal signal with some measurement in terms of the hysteresis loop, I can actually obtain the fatigue information of the behavior of material thermically. It means that I can actually use them locally on the component instead than on the component. If we want, but I mean, that was easy, much worse for aluminium, because aluminium actually, yes, it should work like that, but this is the temperature change during a block of cycles, 20 cycles. You can see that there is no mean temperature change. There's nothing actually that we can measure inside. So the only way to analyze the data was just with thermoelastic analysis. So this is the second harmonic temperature change in terms of signal instead of temperature. And you can see, okay, I didn't say you that actually for aluminum and titanium, the second harmonic is not really straight. It's there is a small second order effect, but we can actually compensate this because it's just goes with the quadratic function. So you can see there is here the points are going as forecasted by theory. Here actually they are behaving in a different way. So this is the fatigue limit. But again, let's concentrate on this data to see actually if we can use them in some ways to predict the behavior of some components. We perform an SN curve with a limited number of specimens, so we obtain the curve. So what we did is we entered this curve with load. We obtained the number of cycles that actually the SN curve will forecast for this method, and we enter with we gave this value to this to the point obtained thermically. So what we obtain, and that thermically speaking, with the stepwise method, we have an information that is absolutely coherent with the SN curve. Okay, one would say, of course, I mean, you calibrate with the SN curve. Yes, of course, but at least you can see that all the points are very well alienated, so there is no really a huge standard deviation. It means that there is a good correlation. And again, the SN curve is on coupon. You can use this data on your component. That is something completely different because all these measurements are local, are not global. The last thing, and then I will go to the conclusion. I wanted to show you just one welded joints. We have been working with a lot of welded joints, but just one, because in terms of mechanism of failure, actually everybody is showing this since this morning, that the behavior of the fatigue behavior of additive manufacturing component is actually well conditioned by the presence of the defects. So it's something that is intermediate between the base material and between welded joints. But I have to say that this technique that is actually working very well also for welded joints. This is the second harmonic signal we obtain for this aluminum. And again, if we go to the SN curve and thermal SN curve, again, we have an excellent correlation between the two. So even for welded joints that are in a way much worse to predict in terms of fatigue behavior, actually we are able to obtain local data that are able to predict the behavior of the material. So conclusion, we are now started to work in terms of fatigue characterization also on additive manufacturing components, and then the idea is to go to the components. We are open for collaboration about that, also because we have some difficulties with the equipment, loading machine above all. But it could be very interesting to merge the experimental data and merge the experimental approaches in order to have a larger overview of what's happening to the material. The advantage of obtaining of using thermal methods again are the fact that with thermoelastic stress analysis we are obtaining also the stress map on the component whilst we are just monitoring the behavior during the fatigue. We have many parameters to study the fatigue behavior, not just one. So the approach is really robust, and we can perform damage analysis. The idea is now to move from the coupons to the components and to apply and verify that what actually I was telling you in the last slide, that it means that you can use thermal SN curve to assess the fatigue behavior and to monitor the fatigue behavior of the additive manufacturing component is actually feasible. I thank you very much for your attention. For any question, or you can contact me via email or by phone. I will be really glad to answer you.